Hello and welcome to the MAML Manual. I'm Sebastian.
And I'm Iris.
And today we'll be covering Meet number 1, topic number 3, Matrices, Determinants, and Systems of Equations. Without further ado, let's jump right into it. Before we even jump into some practice problems of matrices, determinants, and systems of equations, I think it's important to understand what a matrix is. So let's do that right now. So, what is a matrix? Well, the formal definition, and I'll read it from here, a matrix is a set of numbers arranged in rows and columns so as to form a rectangular array. The numbers are called the elements or entries of the matrix. So that's the formal definition, and as you can see here, that's what matrices are. They are numbers in arrays. The important thing about matrices is to understand how we name them, specifically how we name their dimensions. And the reason why it's important to understand this is because we can only perform certain operations with matrices when they meet certain conditions with their dimensions. And I'll specify what this means later on in this video, but for now we just need to understand how we name matrices given their dimensions. So we always start with rows and then we move on to columns. So this one it wouldn't really matter because it has 2 rows and 2 columns, so it's a 2 by 2 matrix, but it does matter to distinguish the other two. So this one right here has 3 rows, 1, 2, 3, and 2 columns, 1, 2. Therefore, we call this a 3 by 2 matrix. This one over here is a 2 by 3 matrix because there are 2 rows and 1, 2, 3 columns. So that's a 2 by 3, this is a 3 by 2, this is a 2 by 2. That naming convention is what every mathematician uses and is really important, especially when we get into matrix multiplication. Now, normally in these videos we do 9 practice problems, 3 of each difficulty, but this video we're actually going to do 10 because there's just so much to unpack, and so I thought that we should include 4 problems of the hardest difficulty, just to really get exposure to this topic, because there is so much to it. And first is matrix multiplication. So this asks you to find the following product and gives you 2 matrices like this. And clearly they are not the same dimensions. And if we're following the naming conventions that I just told you, this would be a 2 by 4 matrix because it has 2 rows and 4 columns. And this would be a 4 by 2 matrix because it has 4 rows and 2 columns. Now, I'm going to explain the process of matrix multiplication, assuming that you haven't seen it before in your life. If you have seen it, then this is going to seem a little bit slow and you're not going to need to watch this full explanation. So you can probably just skip ahead until I get into actually solving the problem. But if you're completely new to this, then I recommend you pay attention to this whole thing. And this is just one example. We will do multiple examples of matrix multiplication. Let's say we have matrix A times matrix B. For us to be able to multiply these together, certain things need to be true about the dimensions of A and B. Let's say for matrix A, we have the rows of A by the columns of A. Let's say for matrix B, we have the rows of B by the columns of B. Now, this is what must be true. These 2 central numbers, the columns of A and the rows of B, must be equal to each other. If these 2 numbers are not equal, then the multiplication operation is invalid. You will not be able to solve it. The only way that you can multiply 2 matrices is if the columns of the first one equal the rows of the second. And I mean in terms of numbers, not in terms of the actual things inside of them, but the amount. The amount of columns equals the amount of rows. The resulting matrix of A times B, so if A times B equals C, the resulting matrix will have the amount of rows that A had and the amount of columns that B had. With this in mind, let's see if this problem is a valid matrix multiplication. As I said before, this first matrix is a 2 by 4 because it has 2 rows and 4 columns. The second matrix is a 4 by 2 because it has 4 rows and 2 columns. These 2 middle numbers are the same. Therefore, this is a valid matrix multiplication problem. The resulting matrix will be a 2 by 2. It will have the amount of rows as the first matrix and the amount of columns of the second matrix. So whatever we get as our answer here needs to be a 2 by 2 matrix. Now, with this in mind, let's actually get into solving the problem. This is the process. You always are looking at the rows of the first matrix and the columns of the second matrix. And this is what you're going to do. You are going to multiply this 4 by this -1. So we get 4 times -1. Then we are going to add 2 times the 3. Then we're going to add the -2 times the 2. So we're going to add the -2 times the 2. And finally, we're going to add the -1 times the -4. Okay? -1 times the -4. So let's do that. 4 times -1 is -4. 2 times 3 is 6. -2 times 2 is -4. -1 times -4 is +4. So after all that, the -4 and the +4 cancel. -4 plus 6 equals 2. So we've got this answer of 2, but what do we do with it now? Remember, before I started doing this work, I told you our answer would be a 2 by 2 matrix. So I'm going to write our 2 by 2 matrix over here. This 2 that we just calculated goes in the first row and the first column of the 2 by 2 matrix. The reason for that is this. In this process, we did the first row of the first matrix and the first column of the second matrix. So row number 1, column number 1 goes in row number 1, column number 1. So that whole process goes in row 1, column 1, and the answer is 2 there. Okay? So now we have to repeat this process 3 more times to get our 3 other entries of the matrix. Okay, to find the entry in row number 1, column number 2, we're going to do the same process, but with row number 1, but with column number 2 now. Okay? So 4 times 0 would just be 0, so I can write 0. 2 times -1 will be -2. -2 times -2 is +4. And -1 times 0 is 0. So 0 minus 2 plus 4 plus 0 is just 2. So for this one, the answer is also 2. For row number 1, column number 2, it's also 2. Now let's do the second row and the first column. -2 times -1 will get us 2. 2 times 3 will get us 6. 1 times 2 gets us 2. 2 times -4 gets us -8. 2 plus 6 plus 2 minus 8 equals 2. So for row number 2, column number 1, our answer is also 2. All right, let's calculate the last entry. Row 2, column 2. -2 times 0 is 0. 2 times -1 is -2. 1 times -2 is -2. 2 times 0 is 0. So for this one, -2 minus 2 is -4. Now that's a little bit surprising. I was expecting the last one to be 2 as well to make it a full matrix of just 2's, but no, this is -4. So our final answer is this matrix right here. 2, 2, 2, -4. That was a long one just because I really took the time to explain matrix multiplication, how we do it, and if it's even valid. The conditions that the 2 matrices need to meet in order for the operation to be valid. Now that you know matrix multiplication, I won't take as much time to go through it step by step. I'll just, do it quicker and show you in the next problems. All right, let's go to the next problem. So remember, this topic is matrices, determinants, and systems of equations, meaning that we can also have systems of equations on this. It's not just matrices. Now, hopefully you have some familiarity with systems of equations, so it won't be as time intensive as learning matrices, but it's still important to review this and be confident with it. So let's do that. So we have these two equations, and to me it looks like it's going to be easiest to use the process of elimination. What I'm going to do is multiply that top equation by 3. So everything in that top equation I'm going to multiply by 3. So I get 9x plus 6y equals 9. On the bottom equation, I'm going to multiply everything by 2. So I get 4x minus 6y is equal to 56. Now this is important that we have a 6y and a negative 6y, because I can then add these equations, and the 6y and the negative 6y cancel out to 0. So I have no more y variable and only have an x variable. This is good because I can solve for x now. 9x plus 4x is 13x. 9 plus 56 is 65. So 13x equals 65. X is equal to 5. Now I can go back into one of the equations and solve for y. 3 times x is 3 times 5, which is 15. So 15 plus 2y is equal to 3. If we subtract the 15, we get 2y is equal to negative 12, or y is equal to negative 6. So we have our answer, x equals 5, y equals 6. To confirm it, you can plug the numbers in. 3 times 5 is 15, 2 times negative 6 is negative 12, 15 minus 12 is 3. 2 times 5 is 10, minus 3y, so negative 3 times negative 6 is 18, so 10 plus 18 is equal to 28. So these are the correct answers, so it would be x equals 5, y equals negative 6, and that would be our answer. Alright, here's our third problem of the video. It's another matrix multiplication problem, but then there's this word thrown in here called determinant. Now the determinant of a matrix is important because it helps us determine the inverse of a matrix, at least for 2 by 2. Because in MAML at least, we only take the inverse of a 2 by 2 matrix. We don't really go beyond that. It might be one of the hardest problems on the team section, but I've never seen an individual problem where you have to take the inverse of a 3 by 3 matrix. So the determinant, I'll show you what the determinant is once we complete the matrix multiplication. Now it's important to note that the only matrices that have determinants are square matrices. And a square matrix is where the number of rows is equal to the number of columns, such as both of these. Both of these are square matrices, they're 2 by 2s. Now that we've got that information out of the way, let's solve this problem. First, I'm just going to confirm with you that this is a valid matrix multiplication. It's a 2 by 2 times a 2 by 2. So those two middle numbers are the same, and the resulting matrix will also be a 2 by 2. So not very exciting there. We just 2 by 2, 2 by 2, 2 by 2. So let's solve. First, I will start with row number 1, column number 1. 2 times 3 is 6. Negative 1 times negative 2 is 2. 6 plus 2 is 8. Now I'm going to move on to row 1, column 2. 2 times 2 is 4. Negative 1 times 0 is 0. So the entry here is 4. Good. Now let's go to the second row and first column. 0 times 3 is 0. Negative 4 times negative 2 is 8. So our entry here is 8. And lastly, we have our second row and our second column. 0 times 2 is 0. Negative 4 times 0 is 0. So our entry is 0. Now this is our resulting matrix. If the problem had just asked us to multiply these two matrices, that would be our answer. But it's telling us to find the determinant of this matrix. Now, the determinant has a simple formula, at least for a 2 by 2. The formula is this: AD minus BC, where we have 2 by 2 matrix A, B, C, D. Now the reasons for this are because of how it works with an inverse matrix. I'm not going to derive that formula and show you why this is the determinant. Just know that it is and know how to calculate it. That's really all you need to know for the purposes of the competition. It is interesting to learn more about why this works. Just the scope of this video, I'm not going to cover it. Okay? So AD minus BC, we come over here. AD, well, 8 times 0 is just 0. And now the BC. BC, 4 times 8 is 32. So we do 0 minus 32, and we get negative 32. So the answer, the determinant of the product of those matrices is negative 32. And that is our answer. Okay. So this question is just asking us to find the product here. Now, it's not harder in that the process of matrix multiplication is the same. It's just a longer process, and it's easier to make an arithmetic mistake. So we'll go step by step and make sure that we don't make such an arithmetic mistake. Okay, so just to confirm that this is a valid matrix multiplication, let's look at these dimensions. So this is a 2 by 3 matrix because it has 2 rows and 3 columns. This one is a 3 by 3 matrix because it has 3 rows and 3 columns. So these two middle numbers are the same, therefore it's a valid matrix multiplication. And the resulting matrix will be a 2 by 3. So over here I'll draw a nice 2 by 3 for us, and that will be our resulting matrix. Okay, now let's go through this. At this point, I'm not going to write out each individual step just because I think we're getting more comfortable with the process of matrix multiplication. So I'll just say it aloud and you can follow along. So row number 1, column number 1, we have 3 times 9, which is 27, 5 times 2, which is 10, and 2 times negative 3, which is negative 6. 27 plus 10 minus 6 is 31. Now, row 1, column 2. 3 times 4 is 12, 5 times negative 5 is negative 25, and 2 times 7 is 14. 12 minus 25 plus 14 is 1. Now, row number 1, column number 3. 3 times negative 8 is negative 24. 5 times 6 is 30. 2 times 4 is 8. Negative 24 plus 30 plus 8 is 14. Took me a little bit to think about that one. Now for row number 2, column number 1. Negative 1 times 9 is negative 9. 6 times 2 is 12. 7 times negative 3 is negative 21. Negative 9 plus 12 minus 21 is negative 18. Row number 2, column number 2, negative 1 times 4 is negative 4, 6 times negative 5 is negative 30, and 7 times 7 is 49. Negative 4 minus 30 plus 49 is equal to 15. And the last one, row number 2, column number 3, negative 1 times negative 8 is 8, 6 times 6 is 36, and 7 times 4 is 28. 8 plus 36 plus 28 is 72. All right, with all of that complete, it's not asking us to do anything else with this matrix, so that is our answer. You can see when the dimensions of the matrices get larger, it gets easier and easier to make arithmetic mistakes. With these types of problems, it's really, really important to just be careful and make sure that each entry is correct. Now, if you know how to do the process, then making one small arithmetic mistake, it's not the end of the world. Like, if you don't get the 4 points on this problem because you got one of the cells wrong, it's not that you don't know how to multiply matrices. You still know how to do it. And that's the important part. I always tell my teammates this too. It's a much worse feeling to be at a math meet and look at the problem and not know how to do it at all. Don't even know how to approach the problem. I've been there. There have been 5 pointers along the way that have stumped me, and as a freshman, there were 3 pointers along the way that stumped me. So it's much better that you know the process than get everything correct. Now, the goal is to get everything correct. I want you to be careful in these operations. But at the end of the day, if you get one of the cells wrong in a math meet, it's not the end of the world. You still know how to do it. It's just, you were rushing, you were under pressure. It's okay. So without further ado, let's move on to the next problem. Okay, so here's a 3x3 system of equations. Given the equations 3x plus y equals 17, 5y plus z equals 14, and 3x plus 5z is equal to 41, what is the value of the sum x plus y plus z? Now, there are a few ways to do this. Of course, you can do elimination, you can do substitution. Those are the two standard methods. I generally like to go for elimination. There is an easier way to solve this problem, and it's this specific problem. It wouldn't work on every problem, but it does work on this one. I'm going to solve it by elimination first, the way I would normally do it, but then I'll show you the shortcut that really only works for this problem. Okay, so let's start here. We have 3x plus y equals 17, and we have 5y plus z is equal to 14. Now what I'm going to do is I'm going to make the y's of these two equations cancel out so that I'm left with an equation in terms of x and z. And when I'm left with an equation in terms of x and z, I'll be able to use x and z, I'll be able to use that equation and compare it with this one to solve for x and z. So basically we're making this 3x3 problem into a 2x2 problem. So let's do that. The easiest way I see is just to multiply this top equation by 5. So I get 15x plus 5y is equal to 85. And then I have 5y plus z is equal to 14, and I'm going to move this 85 over. So if I subtract these equations, because I need the 5y and the 5y to cancel, I'm left with 15x minus z is equal to 71. Up here we have the equation 3x plus 5z equals 41. What I'm going to do is multiply this equation by 5 to get the x's to cancel. I'm going to want the 15x to cancel with the 15x. So multiply that equation by 5. I get 15x plus 25z is equal to 205. And I'm going to subtract these, so the 15x's will cancel. Negative z minus 25z is negative 26z. 71 minus 205 would be negative 134. And now divide both by negative 26. Divide both by negative 26. And we're not going to get great numbers as our result. So z will be 134 over 26, which is equal to, that would be 67 over 13. Not a whole number, not a great result, but that is correct. Z is equal to 67 over 13. Okay? Now, using this, we can solve for x. If we just go to this equation right here, 3x plus 5 times 67 over 13 is equal to 41. We're going to have to write everything in terms of 13s, which is not great. Or 13ths, rather. So 39 over 13x plus, goodness, 335 over 13 is equal to 533 over 13. Once we have this, we can subtract the 335 over 13 to the other side. So we get 39 over 13x is equal to 198 over 13. And so 39x equals 198. X is equal to 198 over 39. Both the top and the bottom are divisible by 3. So we can say that this is instead 66 over 13. So z is equal to 67 over 13. X is equal to 66 over 13. Now let's find what y equals. Well, we can use either equation. Let's just use this one because it's a singular z. So we have 5y plus 67 over 13 is equal to 14, which would be 182 over 13. So we can subtract the 67 over 13 to this side. So we get 5y is equal to 115 over 13. divide both sides by 5, we get that y is equal to 23 over 13. 23 over 13. So everything's in 13ths, which isn't great, but these are correct, and we can add them up like it tells us, x plus y plus z. So let's do that. X is equal to 66 over 13, y is equal to 23 over 13, z is equal to 67 over 13. I see that 67 plus 23 will be 90. 90 plus 66 gets us 156. So the sum would be 156 over 13. And this is actually divisible by 13. We get the answer of 12. So look at that mess. Using the process of elimination, I get that the answer is 12. And that's a perfectly valid way to do it, although it did take me quite a while. So there is an easier way to do it for this specific problem. Now, the first time I did it, I did not see this. I solved it this way. I didn't see the shortcut, but it's kind of a neat shortcut, and I will show you how to do it. So I'm going to erase this, and it's going to be gone like that. How was that transition? It was good, maybe? First time trying it. We'll see how it goes. Here's the shortcut. Let's take all the equations. 3x plus y is equal to 17. 5y plus z is equal to 14. And 3x plus 5z is equal to 41. And let's add all of the equations together. When we add all the equations together, we will get another true equation. We're not messing with these, we're just finding a new equation that also is true. So 3x plus 3x is 6x, y plus 5y is, 6x, y plus 5y is 6y, z plus 5z is 6z, and 17 plus 14 plus 41 is 72. Notice this, 6, 6, 6, they're all the same number. So we can reduce this to be an equation in terms of x, y, and z. X plus y plus z without any coefficients. And that's what they're asking for in the problem. They're asking you for x plus y plus z. So if we divide all of these by 6, we get x plus y plus z is equal to 12. Without the lengthy process of elimination and without actually solving for x, y, or z. Notice, in this process, we didn't solve for x, y, or z. We just solved for their sum. We added the equations together and solved for the sum. So we're able to get our answer in a much quicker fashion. And now this would be for someone who had a really keen eye and is just like, hey, notice how all of the x's, all the y's, and all the z's all have coefficients of 6 if we add them together. Let's see what happens if we do. And once you do that, you can see, oh hey, just divide that equation by 6 and get the answer. I did not see that at first. I don't think many people saw that at first, but this is just another strategy to solve the problem. Okay, with that out of the way, let's move on to the next problem. Okay, here's our next problem. It has both matrix multiplication and matrix addition. Now, just a few quick things about matrix addition. It's not difficult, which is why I didn't talk about it previously in the video. They're never going to give you a question of just matrix addition. It'll be something like this where it's attached to the end of the problem because it's an easy enough concept. So this is what you need to do. Let's say we have a 2 by 2 matrix, 5, 2, 1, negative 3, and we're adding it to 2, negative 1, 5, 7. One key note, if these matrices don't have the same dimensions, then you can't add them. So it's not like matrix multiplication where you need to compare the two middle numbers. It's just if they don't have the same dimensions, then this doesn't work. So it could be a 5 by 7 plus a 5 by 7. It could be a 1 by 2 plus a 1 by 2. It could be a million by million 1 plus a million by a million 1. It doesn't matter so long as the matrices have the same dimensions. The reason for this is the cells or the entries correlate on a one-to-one basis. So the answer will also have the same dimensions, and row 1, column 1 plus row 1, column 1 equals row 1, column 1, and that would be 7. So it's very basic. You just add the corresponding entries to one another and you get the result. So 2 plus negative 1 is 1, 1 plus 5 is 6, negative 3 plus 7 is 4. So that would be our answer. And subtraction works in a similar way. It's just that instead of adding the cells, you would subtract the cells. Okay, now that we know how that works, we can do this problem. Let's do the multiplication first because we won't be able to do the addition without the result of the multiplication. So just to confirm that this is a valid matrix multiplication, the first one's a 2 by 3, the second one is a 3 by 2, and those two middle numbers match up, and we're left with a 2 by 2 as a result. And this is good because if it weren't a 2 by 2, then we wouldn't be able to add it to the 2 by 2 over there. So I'm glad that we're finding that the result is going to be a 2 by 2. Otherwise, this problem would be invalid. Okay, so now let's do that quickly. 4 times negative 3 is negative 12. Negative 1 times 2 is negative 2. 3 times 4 is 12. So our result there is negative 2. Row 1, column 2. 4 times 2 is 8. Negative 1 times 5 is negative 5. 3 times negative 3 is negative 9. 8 minus 5 minus 9 is negative 6. Okay, row 2, column 1. Negative 5 times negative 3 is 15. 2 times 2 is 4. 1 times 4 is 4. So 15 plus 4 plus 4 is 23. And last one, row 2, column 2. Negative 5 times 2 is negative 10. 2 times 5 is 10. 1 times negative 3 is negative 3. So the answer is just negative 3 for that one. Okay, so that's the answer to the matrix multiplication. Now we need to add it. So, and again, it's just look at corresponding entries and add them together. So negative 2 plus 5 is 3. Negative 6 plus 7 is 1. 23 plus negative 23 is 0. And negative 3 plus 5 is 2. So, after doing the multiplication and the addition, the answer is 3102. Let's move on to the next problem. All right, we have reached the hardest problems in this category, the 5-pointers. And now this involves taking the determinant of 3 by 3 matrices, and actually we'll see a problem later on that deals with taking the determinant of a 4 by 4 matrix. So again, this process, taking the determinant would help us find the inverse matrix, but the process also involves other complicated steps that MAML doesn't expect us to know. So we don't have to know how to take the inverse matrix, or how to find the inverse matrix of a 3 by 3. So there are 2 ways to take the determinant of a 3 by 3 matrix. There are more ways, but these 2 are the ones that I know, and they're pretty common. One is the longer way, but it's important to understand it because it's applicable to higher square matrices. So it's not just a 3 by 3 that it's applicable to, but you can go to 4 by 4, 5 by 5, 6 by 6, etc. And then there's one method that's only specific to the 3 by 3 matrix. It's faster, but it also is it's limited to this one case. So let's work on that. Ignoring this problem for now, let's just take the determinant of a 3 by 3 matrix. So this is how it goes. Let's have our matrix. We have A, B, C, D, E, F, G, H, I. This is the process. You come to this first row and look at this first entry A. And you write it down here. Now, ignore all of the other entries in the same row and the same column. So you're going to ignore B and C and ignore D and G. So you're left with E, F, H, and I. And what you want to do is take the determinant of that matrix. So it's A times the determinant of E, F, H, I. And remember, taking the determinant of this one would be E times I minus F times H. We learned how to take the determinant of a 2 by 2 matrix in a previous problem. So that's the first step. Then you move on to the next entry, B, And you do the same thing. You ignore the entries in the same row and the same column. So you ignore A and C, you ignore E and H, you're left with D, G, F, I. And what you're going to do here is subtract B and multiply B by the determinant of D, F, G, I. Now move on to your final step. You're going to look at this third entry, C. Ignore the entries in the same row and the same column. So ignore A, B, and F, and I. And you're left with D, E, G, H. So you're going to add C and multiply C by the determinant of D, E, G, H. And this, when you do all that out, would get you the determinant of this matrix. Now, you don't necessarily have to start at this first row. You can do the same process starting at a different row. But this is what's important to note. If you want to do that, be careful of this. If you want to start on another row of this matrix, you have to keep this sign map in mind. I'm not sure exactly what this is called. I just kind of call it the sign map for the 3x3. I'm sure it has an official name, but we're just going to roll with that for now. So it goes plus minus plus, minus plus minus, plus minus plus. So starting on this first row, we have a positive, a negative, a positive. But if you were to start on the middle row, you would have to start with the negative. The middle term would be positive, and the final term would be negative. If you started on the last row, it would be the same as the first row, where it would be positive, negative, positive. So just be careful. If you're taking the determinant of a 3x3 matrix and you want to start in the middle row, then you have to start with the negative. And the reason you would want to start in the middle row is if there are a bunch of zeros there. Because it's ideal to get a row where there are zeros. Because if there's zeros, then these numbers out here, the A, the B, and the C, would be 0, and you don't even have to take the determinant, because anything times 0 is 0. So say this middle row had like 2 zeros and a 5, you would want to pick that row. You would just have to make sure to use the correct signs for that. Okay, now that we know that method, let's learn the shortcut method. So this shortcut method, I like to call it the diagonal method of taking the determinant of a 3x3. It only works for 3x3s. Again, I can't stress that enough. Don't try this for a 4x4 or beyond. Only works for 3x3s. So let's have our matrix. We have A, B, C, D, E, F, G, H, I. And what I'm going to do is I'm going to write these first two columns outside the matrix over here. So that first column is A, D, G, and that second column is B, E, H. Now I have my setup, and this is what I'm going to do. I'm going to take this first diagonal, A, E, I, and multiply them together. A, E, I. And I'll put this in parentheses because we're going to have an expression on the top, an expression that we're going to subtract from it. So A times E times I, then we're going to add that to BFG. Add that to BFG. And finally, we're going to add that to CDH. So you can tell why I call it the diagonal method. Once we sum that, we're going to subtract the following. And we're going to go in the opposite order. So we're going to go this way. CEG plus AFH, and this is where it starts to get a little bit messy, AFH plus the final diagonal BDI. So that's our determinant. AEI plus BFG plus CDH minus, in parentheses, the CEG plus the AFH plus the BDI. Now, this versus the other one that I showed you, this doesn't look too much simpler than the other one, but it's important because the other one that I showed you, the first method, still had determinants. So you got that equation, or you got that expression, but then you still had to take 3 determinants. In this case, it's just, bam, you're done. Once you have these products, you don't have to take any determinants, you're done. And so once you get the hang of it, this process is much faster than the first process, but it's good to know the first process because again, that scales up. You can continue that process with 4x4s, 5x5s, and so on. Now, I've only seen MAML ask about a 4x4. I haven't seen them ask about a 5x5 or beyond. And actually, later in the video, we will tackle a 4x4 determinant. So stay tuned for that one. But now that we know how to take the determinant of the 3x3 matrix, let's do that here. So the question is asking you, find all values of k such that the determinant of this matrix, which has 3 entries with k in it, equals 9. Okay, so first let's evaluate the determinant, and whatever we get, we have to remember to set that equal to 9. Okay, so we're not done when we do the algebra to get the determinant. We need to set that to 9 and then solve for k. Let's start with the determinant here. I'm going to do the shortcut method, the diagonal method. You could do it the other way, but I find that it takes longer. So I'm going to use the diagonal method here to solve for this determinant. So let's do that. And honestly, you don't even need to write the vertical bars. So those vertical bars represent taking the determinant. But when we're doing the diagonal method, they kind of just get in the way, so we don't even need to write them there. So 2, 3, negative 4, k, negative 3, 2, 1, negative k, k. And then rewrite the first two columns. So rewrite 2, 3, negative 4, and then rewrite k, negative 3, 2. So again, let's start with this first diagonal. 2 times negative 3 times k is negative 6k. K times negative k times negative 4 is 4k squared. 2 times 3 times 1 is 6. And we're going to subtract 1 times negative 3 times negative 4, which is 12. 2 times negative k times 2, which is negative 4k. And k times 3 times k, which is positive 3k squared. So when we subtract this, we get 4k squared minus 3k squared, which is k squared. We get negative 6k minus negative 4k, getting us negative 2k. And we get 6 minus 12, which gets us negative 6. Now that's the determinant, and that's perfectly fine, but we need to set it equal to 9 to solve for k. So we've solved for the determinant, but now we need to set it equal to 9 so that we can solve for all the possible values of k. So we get k squared minus 2k minus 6 equals 9. Subtract 9 from both sides, we get k squared minus 2k minus 15 equals 0. And now we have our little factor x over here. They need to multiply to negative 15 and add to negative 2. So the two numbers that do that are negative 5 and positive 3. So negative 5 and positive 3 satisfy that. So our factors are k minus 5 and k plus 3. So our answers are 5 or negative 3. After this lengthy problem, you now know how to take the determinant of a 3x3 matrix in two different ways. I like this way more, but whatever you want to do is fine, so long as you get used to it and you can do it under time pressure. All right, with that out of the way, let's move on to the next problem. Okay, here's a similar problem where we have to take the determinant of this expression, and once we find that algebraically, we set it equal to 57 and solve for x. So let's do that. So we're going to do and this one's a little bit different because we have an x plus 1 factor, which we didn't have in the previous problem. We only had k's or negative k's. But that's okay, it's the same process of solving it, so that shouldn't trip us up too much. So let's make our setup. So we have x, 1, negative x, x plus 1, 1, 3, x, 4. Repeat the first two columns. X, 1, negative x, x plus 1, 1. Okay, let's get that started. 4 times x plus 1. I'm just going to write that up here so that I can distribute it. We get 4x squared plus 4x. So that first term is 4x squared plus 4x. Then we get negative x times negative x, which is x cubed. So we're going to have to solve a cubic in this one, which is great. And then we have 3 times 1, which is 3. Subtracted from this, we get negative 3x times x plus 1. So distributing that, we get negative 3x squared negative 3x squared minus 3x. So negative 3x squared minus 3x. And then we get just x squared with that term. And then we get here a minus 4x. Okay, simplifying the parentheses before actually subtracting the two, I get x cubed plus 4x squared plus 4x plus 3 minus, and in these parentheses, the negative 3x squared plus x squared turns into negative 2x squared, and the negative 3x minus the 4x turns into negative 7x. Okay, when we combine this, we get the expression x cubed plus 6x squared plus 11x plus 3 is equal to 57. Okay, now we need to solve a cubic here. So we subtract the 57 by both sides. We get x cubed plus 6x squared plus 11x minus 54 is equal to 0. All right, so now we have here a cubic equation that we need to solve. The technique for solving this will come later. I kind of want to teach you that more in like polynomials down the road or when it shows up in later topics. So this one will be tough. It is a 5-pointer. It would suck to get to this point and not know how to solve it. So if you do want to research that on your own before I make my own video on that, you would need the rational root theorem and synthetic division to solve this. If you already know what that is, great, you'll follow along with me. I'm just not going to teach it in this video. I'll teach it later on. So, okay. So I'm going to do synthetic division here. So I have the coefficients, 1, 6, 11, negative 54. And I'm just going to test out some numbers until I get a remainder of 0. Let's see. If I had 2, it would be 1, 2, 6 plus 8, 16, 27. That actually works. I'm surprised. I was not expecting my first guess to work, but let's do it. Okay, so 2 is our guess. We bring the 1 down, multiply it. We have 2 here. 6 plus 2 is 8. 2 times 8 is 16. 11 plus 16 is 27. 27 times 2 is 54. 54, or negative 54 plus 54 is 0. So after synthetic division, we are left with x squared plus 8x plus 27. And I can use the discriminant to see if this has any real zeros because we're only looking for real numbers of x. So the discriminant would be b squared minus 4ac, which in this case would be 64 minus 4 times 1 times 27. So that would be 64 minus 108. And 64 minus 108 is a negative number, so the discriminant is negative, and therefore this quadratic has no real solutions. So our only real solution is 2. So our final answer is x equals 2. Okay. If you don't know this stuff, that's okay. We'll cover it later on in future topics. Okay, let's move on to the next problem. All right, here's our second to last problem of the video. Normally this would be our last one, but again, I mentioned how I'm doing 10 problems this video because there's just so much to unpack in this topic, and I think it's worth covering 10. And this is kind of the bonus one that we have. It's the 4x4 determinant. This only showed up once in the entire in all of the problems that I've seen from this topic. This has only showed up once. But it's still good to know, and you already know how to solve this problem, because it's just an extension of how to solve a 3x3 determinant. And I'll explain what I mean now. So just like in a 3x3 determinant, you're going to look for a row that has the most zeros. And I can see here that this row has the most zeros, so I'm going to want to use this row. And now I have to be careful of the signs. So the sign map for the 4x4 will be plus, minus, plus, minus, minus, plus, minus, plus, plus, minus, plus, minus, minus, plus, minus, plus. So this second row, it will start with a negative, then go to positive, negative, positive. So that's important to note. Now, these two zeros, I'm not even going to have to worry about them because I know the answer will be 0. So really, I'm just worrying about the 2 and the 1. So it's going to be negative 2. And then I'm going to take the determinant of what remains. So I'm going to get rid of everything in the row and everything in the column. And I'm going to take the determinant of what remains. I'm going to take the determinant of 2, 3, 0, 0, 1, 5, 1, 1, 1. After that, I'm going to add 1 times the determinant of anything that's not in that row or column. So it's going to be 1, 3, 0, 2, 1, 5, 1, 1, 1. Okay. So this isn't too bad. Now all I have to do is take the determinant of 2 3x3s, which isn't the end of the world, especially when they're nice numbers. So let's do that. So I'm going to do this one first. And actually, I'm gonna just do the diagonal method. You could do it either way, especially since there are zeros in this one. It would be easy enough. But I'm going to do it the diagonal method. So we have 2, 3, 0, 0, 1, 5, 1, 1, 1, 2, 0, 1, 3, 1, 1. Now doing that, we get 2 plus 15 plus 0. I drew this a little bit out of proportion, so the diagonals aren't perfect, but it's fine. So on bottom we have 0 plus 10 plus 0. Sorry for the mess up here. So it's 17 minus 10, which gets us 7. So the determinant of this one is 7, so it's negative 2 times 7, which would be negative 14. So I'll just replace that now. Negative 14. And now we have to take the determinant of this matrix. So let's do that using the diagonal method. So we have 1, 3, 0, 2, 1, 5, 1, 1, 1. Now we rewrite the first and second column. Over here we have 1, 2, 1, 3, 1, 1, and we can use the diagonal method. So 1 times 1 times 1 is 1. 3 times 5 times 1 is 15. 0 times 2 times 1 is 0. Subtract 0 times 1 times 1 is 0. 1 times 5 times 1 is 5. 3 times 2 times 1 is 6. So we have 16 minus 11, which is equal to 5. And the 1 times the 5 will get us 5. So our final answer is negative 14 plus 5, which is equal to negative 9. So the determinant of this big matrix is negative 9. And now that's not too bad. We had a row with 2 zeros, so all we had to do was take the determinants of 2 3x3 matrices. So that wasn't bad. If there weren't any zeros, then we'd have to take the determinants of 4 3x3s, which would be more of a pain. But this was simple enough. We got negative 9 as an answer. And as I said, this method scales up. I highly doubt they will ever ask you to take the determinant of a 5x5 matrix, but if they do, this process scales. You will know how to take that determinant. It will be a pain, but you'll know how to do it, which is a good thing. So with that monster of a problem complete, let's go to our final problem of this video. All right, we are at the final problem of this video. This gets into inverse matrices, which is finally where we apply our knowledge of how to take the determinant, and we apply it to something useful where we can take the inverse matrix. Again, I've been doing this a lot this video, but just some background before we tackle this problem. The inverse matrix is kind of like a reciprocal of a number. So let's say we have 9. The reciprocal of 9 is 1 over 9. And if we multiply 9 by 1 over 9, we get 1. So if we had the number negative 1/2, its reciprocal would be negative 2, and we would get 1 as our answer. So just like numbers have reciprocals, matrices have inverses. So if we have matrix A, and we multiply it by its inverse, which we'll think of like a reciprocal, even though it's not, we get I, the identity matrix. And the identity matrix, it only exists for square matrices, but say these were 2 by 2 matrices, the identity matrix would be 1, 0, 0, 1. If it were a 3 by 3, we would extend this to 1, 0, 0, 0, 1, 0, 0, 0, 1. If this were a 4 by 4, we would extend it further to 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. It's a lot of ones and zeros, but the point is, this main diagonal, the one that starts at the top left and goes down to the bottom right, is full of ones, and everything else is full of zeros. That's the identity matrix. So if this were a 4 by 4 matrix, and you multiply it by its inverse, you get the identity matrix, which is this. You have ones along the main diagonal and zeros everywhere else. Well, why is that important? Why do we care about the identity matrix? Well, the identity matrix is special in that if you have a matrix and you multiply it by the identity matrix, you get the same matrix you started with. So if we do a quick example of that with a 2 by 2, if we just have like 5, 7, negative 3, negative 2, and we multiply it by 1, 0, 0, 1, we end up getting 5 times 1 is 5, 7 times 0 is 0, so our first entry is 5, 5 times 0 is 0, 7 times 1 is 7, that's our second entry, negative 3 times 1 is negative 3, negative 2 times 0 is 0, so we have negative 3, and negative 3 times 0 is 0, negative 2 times negative 1 is negative 2. So any square matrix times the identity matrix gets itself as a result. That's why the identity matrix is important. Now that we have some background on inverse matrices and identity matrices, let's get into how we actually solve for the inverse matrix of a 2 by 2. This is the formula right here. If we're trying to find the inverse of matrix A inverse is equal to 1 over the determinant of A times the adjugate of A. The adjugate of A. What is the adjugate of A? Well, it's very, very simple. If this is our matrix, A, B, C, D, the adjugate is D and A are swapped, and the B and the C are turned negative, or they're reversed signs. Notice this here. We are dividing by the determinant. So if the determinant of this 2 by 2 matrix, A, is 0, then it won't have an inverse, because 1 divided by 0 is undefined. So if the determinant of A, a 2 by 2 matrix, is 0, then it won't have an inverse. So now that we know the formula, let's actually apply it to this problem. I'm going to rewrite this. I'm going to say A inverse times matrix B is equal to matrix C. Now we're going to do some matrix algebra here, which is wonderful. That's what we love to do. We're going to do some matrix algebra to solve for A, because that's the point of this question. It's saying there exists only one 2 by 2 matrix A such that this is true. So we're trying to find A. So we need to manipulate this equation to solve for A. So the first thing I notice is that we have an A inverse here. To get rid of that A inverse, we are going to need an A. So what I'm going to do is I'm going to write an A in front of here, but then I'm going to have to do the same thing on this side of the equation. So I'll do that below. So I'm going to move this below. You have to write an A at the front of both equations. So A inverse times B is equal to A times C. This A and A inverse go away, so we're left with B is equal to A C. We want A by itself, so we need to get rid of this C. To get rid of that C, we need C inverse. So I'm going to multiply both sides by C inverse. We get B C inverse is equal to A C C inverse. And the C and the C inverse cancel, so we're left with B times C inverse is equal to matrix A. That's the information we need. So we know that this matrix times the inverse of this matrix equals matrix A. So now we get to solve for the inverse of the rightmost matrix. So as we know, the inverse of C will equal 1 over the determinant of C times the adjacent of C. C, the determinant would be 1 times 1, which is 1, minus 0 times negative 5, which is 0. So this is a nice one. 1 minus 0 is just 1. So the determinant of C is 1. So that's nice. So we're not really doing anything because 1 divided by 1 is just 1. So now all we need to do is find the adjacent of C. So the adjacent, if we remember, A, B, C, D goes to D, negative B, negative C, A. So this, the 1 and the 1 swap, which doesn't really do anything because they're both 1. So the 1 and the 1 swap, and the 0 and the negative 5 swap signs. It doesn't do anything to the 0, but it does change the negative 5 from negative to positive. So our adjacent matrix is 1, 0, 5, 1. And that is equal to C inverse. So now we multiply B by C inverse to get the matrix we're looking for. So B is negative 3, 1, 4, negative 1, and 1, 0, 5, 1. Multiply that by 1, 0, 5, 1 to get our matrix A. So the result is going to be a 2 by 2. A 2 by 2 times a 2 by 2 equals a 2 by 2. Row 1, column 1. Negative 3 times 1 is negative 3. 1 times 5 is 5. Negative 3 plus 5 is 2. Row 1, column 2. Negative 3 times 0 is 0. 1 times 1 is 1. 1 is our entry. 4 times 1 is 4. Negative 1 times 5 is negative 5. 4 minus 5 is negative 1. And row 2, column 2, 4 times 0 is 0. Negative 1 times 1 is negative 1. So we have another negative 1 down there. So that is matrix A. And that is our answer. So that was a lengthy problem, but we learned how to take the inverse matrix and we learned how to do some basic algebra with matrices to cancel things out and get what we're looking for. That was a long video, but we learned so much. We learned what a matrix is. We learned how to multiply matrices in addition to adding matrices and subtracting matrices. We learned how to take the determinant of square matrices. And we learned how to take the inverse of a 2 by 2 matrix. And we also had some system of equation problems in there too, because those do show up in this topic. So it was a lot, but that was the last problem, and I'm glad you stuck around. Alright, after those lengthy 10 problems, that concludes our video on matrices, determinants, and systems of equations.
Thank you for watching.
I'm Sebastian.
And I'm Iris.
And we're the MAML Manual.